So we've already looked at ions and how you can have cations and anions. And so now those cations and anions are going to combine together to form ionic compounds. So the compounds contain the cation, the positive one, and the anion, the negative one. And whenever you combine them together, the cation is always going to go first. So if we look at our first example, we have calcium fluoride. Calcium is a cation, it's a 2+, and fluoride, which we know is just fluorine, but because it's an anion, we changed it to IDE ending. That is going to be listed second in both the formula and the name. Then we have what's called barium hydroxide, and hydroxide is one of our polyatomic ions. You can always tell a polyatomic ion in the chemical formula whenever there's parentheses. So whenever you see parentheses, you know there's going to be a polyatomic ion. Also, you know there'll be a polyatomic ion when you have more than 2 elements. So we have barium, oxygen, and hydrogen. Always an indication of a polyatomic ion. When we look at calcium fluoride, that's just 2 different elements. So therefore, there's no polyatomic ion, more than likely in this one. But whenever you see 3, there's always a polyatomic ion. So all you have to do whenever you name it is you just look up that polyatomic ion on the back of your periodic table, and then you can identify it. Same thing down here. We have K, N, and oxygen, and O. We have 3 different elements, therefore we have a polyatomic ion. And most of our polyatomic ions are going to be anions. So you're going to be looking for the end of the formula. And so NO3 is just nitrate. Then what if we have transition elements in there? Well, we know they're all cations. And so we have to keep the Roman numerals if we need them. So they're always going to be listed first. If we don't need the Roman numerals, then we don't put them in there. How do you know if you need Roman numerals or not? Well, remember on the back of your periodic table, we highlighted the 20 elements that were transition metals that needed Roman numerals. So you only keep the Roman numerals if they are one of the highlighted ones. If they're not, then we're not going to keep those Roman numerals. So we have FeO, so we have iron 2 oxide. And if we look at the next example, we have Fe2O3, which is iron 3 oxide. So looking at those 2 compounds, they both contain iron and oxygen, but we know because of the law of multiple proportions, we can make multiple compounds with the same elements. So these are both made of iron and oxygen. However, they're different compounds because they have different chemical formulas. This is a 1-to-1 ratio. This is a 2-to-3 ratio. Why is that? Because this one has the iron 2 ion in it, and this one has the iron 3 ion in it. And so we have to differentiate between iron 2 and iron 3, and that's why we need to use the Roman numerals, because iron is one of the highlighted ions on the back of our periodic table. Then looking at NiCO3, we see 1, 2, 3 elements, so we know there's a polyatomic ion in there, and we look that up on the back of our periodic table, and we see that it's carbonate. We also see that nickel is a transition element, so it's a good idea to check the back of our periodic table for that one as well, and nickel is highlighted because there's multiple options for nickel, so we have to identify this as nickel 2. Now, how do we know it's nickel 2? Well, because carbonate is a 2-, and so it's going to take 2 electrons. And so that means nickel had to give away 2 electrons because those formulas always have to cancel out. So if we wanted to name MgCl2, Mg is magnesium and Cl is just chlorine. So that would just be called magnesium chloride. We do not need to use the Roman numerals because magnesium is not a transition metal. So it's just in group 2. So it's always a 2+. There's no other choice for that one. And we do need to change the chlorine to chloride. So it would not be magnesium chlorine. Then we have Na2CO3. So we see 3 elements. And whenever you see 3 elements, you know you're going to have a polyatomic ion. So we look at the back of our periodic table and we identify that as carbonate. Sodium is in group 1, so it will never have a Roman numeral because it's always a 1+. There's no other option. So this would just be called sodium carbonate. Then we have NiCl3. So that's just 2 elements, nickel and chlorine. And nickel is a transition metal, so we're going to check the back of our periodic table. Nickel is highlighted, so we do need to use Roman numerals for it, and then chlorine just becomes chloride. So this would be nickel 3 chloride. Then we have WN2, and W is tungsten. It is a transition metal, so you check the back of the periodic table. W is not highlighted, so therefore it would not use a Roman numeral. and N is just nitrogen, so that becomes nitride. So this would just be tungsten nitride. If you put a Roman numeral in there, it would be marked wrong. Then what about writing the formulas? So when we name them, we have to look at Roman numerals. When we're writing formulas, we have to look at oxidation numbers. So oxidation numbers of each of our ions, the cation and the anion, must cancel out. Our cation is still always written first. So if we look at sodium chloride, which is salt, we have sodium, which is a 1 plus because it's in group 1. Chlorine is a 1 minus because it's in group 17. So this is a perfect combination. Sodium wants to give away 1 electron. Chlorine wants to take 1 electron. So our formula is sodium chloride, NaCl. Nickel 2 oxide. So we have a transition metal in here. So nickel has Roman numerals. And the Roman numeral 2 here indicates that nickel is giving away 2 electrons. So that's why we identify this as the 2 plus for nickel. And then oxide is just oxygen, which is a 2 minus. So once again, a perfect combination, 2 plus, 2 minus, that cancels out. So our formula is NiO. Then what if they don't equal out? Then what do we do? Well, all we have to do is add more elements. So this is actually a typo in here, just checking to see if you're paying attention. This is supposed to say sodium oxide, so not nitride, oxide. So sodium oxide contains Na plus and O2 minus. Sodium is in group 1, that's why it's a 1 plus. O is in group 16, that's why it's a 2 minus. And when we try to cancel them out, we have a 1 plus and a 2 minus. So that doesn't work exactly. So we have to add in another sodium with another 1 plus charge so that it cancels out that 2 minus. They always have to cancel out. So our formula is going to be Na2O, this 2 indicating the fact that we need 2 sodiums, each with a 1 plus charge to give away 2 electrons total, and then oxygen will take 2 electrons. They always have to be stable. Then we have manganese 3 fluoride, and the 3 indicates that manganese is giving away 3 electrons. So that's why we have the 3 plus here. But fluorine will only take 1 electron because it's in group 17, so it's a 1 minus. And so we have to make this work. Manganese has to give away 3, fluorine will only take 1. So what we do is we just add in more fluorine so that we'll have 3 plus and 3 minus. So when we have 3 fluorines, we would write this as MnF3. Then another check to see if you are paying attention on here. Calcium nitride contains calcium, which is a 2 plus because it's in group 2, and nitride, IDE, means it's just nitrogen, so that's a 3 minus. So our formula is going to be Ca3, and then that's going to be an N. That is not an F. That's an N, and then a 2, because we have to make those cancel out. So a 2 and a 3, you have to add a little bit of both. So this would be a total of 6 plus because we have 3 calciums, each with a 2 plus charge. And then we have a 6 minus because we have 2 nitrogens and they each are 3 minus. So 6 plus, 6 minus will cancel out. So you just need to add in more of whatever you need to make it equal out. Then what if there are polyatomic ions involved? Well, we treat those as a single ion, just like we would calcium or nitrogen or whatever it would be. And we're also going to use parentheses. This is the only time we would use parentheses, when we need more than one polyatomic ion to cancel our oxidation numbers. We don't use them all the time, only sometimes. So our first example, we don't use them at all. So we have magnesium sulfate. Magnesium contains Mg2 plus. So because it's in group 2, it's a 2 plus. Sulfate, because it ends in ATE, you know it's a polyatomic ion. So you just look at the back of your periodic table and you just look up sulfate. And so the sulfate ion is SO4, 2 minus. And this is a perfect combination, 2 plus, 2 minus. They cancel out. So our formula is MgSO4. In our next example, we have iron 3 hydroxide. So this has a Roman numeral 3 because iron has multiple choices. So it tells you that this is a 3 plus. So this is iron with a 3 plus. So it's got to give away 3 electrons. And then we have hydroxide. So hydroxide is a polyatomic ion. It is one of the very few that actually end in IDE, but we know there's no such thing as hydroxygen. So hydroxide is a polyatomic ion. So you look on the back of your periodic table and you see that it's an OH minus. It's a 1 minus, so it will only take 1 electron. Well, iron's got to give away 3, and hydroxide's only going to take 1. So in order to make this work, we need 3 hydroxides to cancel those out. Whenever we need more than one polyatomic ion, we need to put it in parentheses, whatever that polyatomic ion is. You have to copy it exactly from the back of your periodic table. And then you always put however many you need after the parentheses. So this 3 right here means you need 3 oxygens and hydrogens known as hydroxides. You need 3 hydroxides. So you need to have the parentheses whenever you need more than one polyatomic ion. Same case is true for our next one, calcium nitrate. So you hear ATE, you know that's going to be a polyatomic ion. Look on the back of your periodic table. We have calcium in group 2, so it's a 2+, and nitrate on the back of your periodic table is NO3, 1-. And so our formula has to equal 0, and the only way we can do that is by having 2 nitrates. So we have a 2- total and a 2+ total. So we need to put the nitrate in parentheses. You copy the exact polyatomic ion from the back of your periodic table, put that in parentheses, and then put however many you need on the outside of the parentheses. That's the only way you can write out formulas for ionic compounds when they contain polyatomic ions that you need multiples of. So if we look at sodium acetate, sodium is just Na, it is not S, so do not choose this one or that one. So sodium acetate is Na, it's a 1+ because it's in group 1, and then acetate is or ends in ATE, so we know that it's going to be a polyatomic ion. You look on the back of your periodic table, and you see that acetate is C2H3O2, and it's also a 1-, so this is a perfect combination, 1+, 1-. So we would just go with NaC2H3O2. Then we have manganese 2 carbonate. So this 2 right here means that manganese is going to be giving away 2 electrons, so it's a 2+ charge. And this is manganese, not magnesium, so it would not be Mg. Then our carbonate ends in ATE, so therefore we know it's another polyatomic ion. We look on the back of our periodic table, and we see that carbonate is CO3, and it's a 2- charge. So this is another perfect combination, 2+, 2-, one of each of those. So we would have MnCO3. Then we have aluminum oxalate. So aluminum is in group 13, so it's a 3+. Oxalate ends in ATE, so it's another polyatomic ion. So you look it up, and it's C2O4, and it's got a 2- charge. So now we've got a 3+ and a 2-. So we're going to need some of both to make this equal out. So this one is going to be Al2, and then because we need more than one oxalate, we have to put the oxalate in parentheses, and oxalate is C2O4, and then we put the 3 on the outside of the parentheses, indicating that we need 3 oxalates. And then we have zinc sulfide. So zinc is a transition metal, but it doesn't have a Roman numeral. The reason why it doesn't have a Roman numeral is because it's always a 2+. It is not one of the highlighted ones that we have on the back of our periodic table. So we don't have any Roman numerals here. We just know that's always 2+. And then sulfide ends in IDE, so we know that's just sulfur. So sulfur is in group 16. It's a 2-, so this is a perfect combination, 2+, 2-. So it would just be ZNS. So ZnSO4 would be zinc sulfate, and this one would be zinc sulfite. So you really have to pay attention to which one it is, and this one is sulfide. Then our last one, we've got potassium phosphide. So potassium is in group 1, so it's a 1+. Phosphide ends in IDE, so we know it's just phosphorus. And phosphorus is in group 15, so it's a 3-. And so to make this work, we're going to need 3 potassiums to balance out that 3- charge. And so we would write this as K3P. So from here on out, you're going to need to know how to write out these chemical formulas. Some key things to keep in mind. Always use that periodic table. Look at the front and the back. We wrote lots of different notes on it. You'll be able to use this for all of your tests and quizzes, and it's very, very beneficial for you. It's just a matter of looking it up. And then always remember that those oxidation numbers have to cancel. The pluses and the minuses all have to cancel out.